All right, everyone, we're a little bit late here. Let's go ahead and get started. Again, I have some notes. I got enough for the whole time to go over some things about calculating delta G and delta A for your gas experience and gas contraction. Again, a big part of the second test. And then I have just derivation after derivation example that instead of like the HDP, I've got the HDV, and you just make, so it'll be very clear what to do. Every now and then, so when I make those shifts though, from V to P, that's kind of an easy way to go. It does sometimes make the question much harder or much easier. I generally go with easier, and I'm going to do harder, but that's not always true. So just look out for that. So again, my point is, when I change a V for a P, it really can change the amount of steps you have to do in the problem. So just be a little wary of that. As usual, would someone like a little candy? Their questions? Or you just want the candy?
Both.
Okay, so we'll do that. There you go.
In the equation that you just put on the board for component and phases to calculate delta G, can you show using that equation why at equilibrium delta G is 0?
Probably not, no. That I would do with the Clausius inequality to show that at constant T and P, remember that's crucial, constant T and P, total entropy is, delta G is total entropy times, change in total entropy, or third again, constant P, the change in Gibbs energy is the change in total entropy times minus T. So change in entropy, total entropy must be positive. It's been multiplied by a negative number, therefore delta G must be negative. Now that's for a spontaneous thing. An equilibrium thing has total entropy change of 0. And so that's why delta G is 0. I kind of used that when I said that equilibrium chemical potentials are equal. I used that. So I can't then go backward, right?
Okay.
Yeah, that doesn't work.
Okay.
So, all right, another question? Oh, or you just wanted, yeah. There you go. Look out, everyone. I'm really bad at this. Any other? We're okay? Quick question?
Going back to enthalpy, PV term to U. What effect is being added or subtracted from U to get enthalpy?
I'm going to say again. What?
I thought the expression for H was U plus PV.
That's right.
What is actually being added or subtracted from U to get H?
Well, okay, hold on. Are you ready? Here it goes.
I think you got to turn
I'm
around.
pretty bad.
In the box, in the bleacher seats.
I should have been in the major league. So now, so what's happening with H? Remember that it's a Legendre transform, and U having a function of S and V is not always useful. So what I'm doing is subtracting the variable I don't want times its conjugate. That just happens to be a negative because IUPAC decided it was a negative. So that's U plus PV. And to decide what that does, you look at the change. You look at the change because that's how you figure out what natural variables are. And now that I've done this, see, I couldn't express this when we first started on this, but now I can. This is the change in U plus PV plus PDP. And so now I've got minus TDS plus VDP. No, why did I say, no, not minus TDS. TDS is positive, sorry, that's heat. My bad, screw up. I'm doing it off the top of my head. And therefore, H is a function of S and P. S and P. And so now, why am I doing that? So you kind of need to look back at my derivation of Legendre transforms. It takes a really long time, so I'm kind of unwilling to do it now. But and even if you don't recall, this is still a legitimate Legendre transform. And I know that this guy is a function of S and V because of this change in S and change in V here. And that's how I know H is a function of S and P because it's right here in front of me. This is how I figure out what natural variables are. So, and why does that matter? It's because they're special. These energy functions are special when you hold their natural variables constant. If you hold them both constant, then the change in H is equal to minus temperature times the change in total entropy. And that's total entropy. And that's, again, by the Clausius inequality. At constant pressure, the change in H was the change in heat. And again, that's very useful because I can start every process with a burn, not with a work. All right, so that's the car, right? We used to do the horse, which we started with a change in work, and now we start with the car, and that's a change in heat. And likewise on all the other functions. And at constant S, I don't know that it's special. It's just VDP. I don't know what you really get out of that, in all honesty. So, does that kind of get it?
Well, I saw that VDP term, and I came across a term called non-expansive work. And I was wondering, is that VDP a definition of non-expansive work?
Yeah. In fact, I should have gone over this, and I just kind of dropped it because I don't like it too much. All right, so G again is useful. G is minus T times change in entropy when T and P are constant. But now again, G, so again at constant T and P, G is minus T total. Again, that's incredibly useful, but a constant T, change in G is work, there's no work, there's only changes in work. That's not PV. That's not pressure volume. Some other kind of work. Now, the best example is electrical work. Because remember, work is, the way the book puts it, just so, just to help you get it, figure out what counts as work, that's when you do something that can lift a weight. Now, again, I can certainly build a motor that turns a crank that lifts a weight, and so that makes a lot of sense. And I can drive a motor with gas, or I can actually hook it up to pressurized gas. That's a certainly legitimate way to build a rotating motor. But I can also connect a battery. And that battery can turn a motor that lifts a weight, so that's work too. So, and this is important because when we do electricity, everything will be done in the form of DG. We are going to do electricity because the government is investing in batteries in a big, big way because we think we're going to make our energy by photovoltaics, that means solar cells, not by splitting. The idea was we're either going to split water into hydrogen and burn the hydrogen, or we'll use photovoltaics, in other words, we'll generate electricity from solar panels. Guess which one? The solar panel one. The government does not think that hydrogen is viable, so the government has largely stopped funding it. So we're going to go with solar cells, but the sun stops shining. So the idea is that what electricity you don't use gets stored in the battery, and then you can use it at night. And that is the future energy plan. Really, they have almost no plan. Your children are going to grow up and like, that Mad Max movie? That's not a movie, that's a documentary, something from the future. So, that's actually true, but that's really sad. It's actually going to be that way. We're going to kill each other with the last drop of oil. We're never going to figure out something better. Sorry for the depression. We want to talk about cancer? But anyway, yeah, that is a good way to put it. It's all work that's not expansive work, so that doesn't count. Question? This is going to hurt. All right. Okay. I got close. I better get it. I'll pick it up later. Otherwise, we're going to have ranks on here.
Yeah, I will do that. For the equation of change of H, the function of S and P that you have in the bottom of there. Now, if we hold S and P constant, wouldn't H be 0?
Well, no, not necessarily. So remember, this is a change in H, and no, it would only be 0 if you're at equilibrium. You know what I have to do here? Right, because that looks like that's 0. I think that I would need to, if I'm holding S and P constant, then what the hell am I doing to begin with, right?
Yeah.
So if I hold S and P constant, then that's a cylinder not moving. Now remember, this I did for a gas expands and gas contracts. If I'm holding these constant, then I'm not doing anything at all, so the change in H would be 0. But at the same time, so it sounds like this is irrelevant. I think what I need to do is tack on that change in mass term. I need to add the chemical potential. So it is relevant, but it will be relevant, again, when I magically hold entropy constant. That, again, I can do adiabatic reversible machines. And I can certainly hold pressure constant. That's not hard. That's the easy way to do things. But what it would be applied towards is a chemical reaction, a change of mass, because I do actually technically have another term here. So I think that's correct. I hope so. So anyway, any other questions or examples? You want examples, right? Yeah? Okay, let's get on. Let's start doing examples. Because I think, well, I hope that the derivations are relatively easy. I think it just depends on your personality type. Are you a calculator person or are you a derivation person? So you may not be the same people. So, examples. Let me point out something that is kind of nuts. Calculate changes in A and G. Sorry, I didn't do that right. So, I did a little bit of this, but let me explain in a little bit better detail about how you do this. Let's do isothermal. So we're still doing a little bit of gas expands and gas contracts. The G is minus SBT. Okay, but that's gone, so that makes our life easier. And here's this term. Okay, now what I did was, if we're isothermal, and again I'm calculating this reversibly, it doesn't matter whether we're reversible or irreversible, because G is a state function. What I can do is nRT, okay, and I'm going to integrate it. Sorry to work backward, I know that may screw up your notes, but I need to kind of hurry. That's nRT lnPF. And now let me point this out because this will be probably on the next homework set. nRT ln, so perfect gas. Just point that out. Minus nRT ln BF. I'm just using that minus ln A over B is ln B over A. Okay, look familiar? What's that?
Delta work.
Huh? Change in what? What did he say? It's reversible work. And notice something that's kind of neat. That was also that's minus the change in S times T. Right? So isothermal, remember, was so this is consistent with delta G is delta H minus T delta S. So I kind of wrote that in reverse. What's delta H when you're isothermal?
0.
Right, 0. Right, see, it all works. You can derive it multiple ways, you get the same thing. So that's kind of neat. Now, delta A is going to be, I'll be very exact. It's going to be integral minus SBT, but again, we're going to be at constant temperature minus PdV. Now that is automatically the change in work. And again, that's reversible work. So I should have said that, but anyway. And remember that this is consistent with A. Delta A is the same as delta G, except I have a U instead of an H. Remember this, but this is also 0, so it all ends up being exactly the same thing. And here's another thing. Sorry, I'm not looking at the board too well. So remember, isothermal, delta A is delta G, which is minus T delta S, which is the change in work. And let me emphasize this reversible work. In case it's irreversible transition, it wouldn't matter. Wait, it wouldn't matter? No, sorry. All right, so if I do an isothermal, okay, so be careful. If I do isothermal irreversible, the reversible work is delta G and A, but the work is not delta G or delta A. It'll be different. Remember, reversible versus irreversible work is different. The reversible work will be G and A, even if the transition is irreversible, and that's the state properties, right? That's the path independence kicking in. Be careful about that. So don't automatically assign G or A to the work. Do this. Okay, that's easy if you just do that, all right, in your set. So look out for that on your homework. Okay, so isothermal, reversible, give me entropies, all three of them. Give me A, give me G. That's 5 more things you got to calculate on the next test and on your present homework. But now, here's a nutty thing. This is nuts. Let's do adiabatic. Delta G and A for adiabatic. Again, I'll use my shorthand. Okay, now here's what's going to happen is you're not going to see me ask this on adiabatic transitions. You will not be asked with delta G, delta A, or adiabatic, because you can't. Well, you can, but it's very difficult. Okay, problem. Let's do delta G and delta A will be the same. Delta G and delta A are just, they're really almost identical. Minus TDS plus VEP. Okay, so, sorry, what's wrong with me? Minus SDT, sorry. Again, you see me go on automatic, I make as many mistakes as you do. I just can get you again. So, I already know that the problem is that temperature changes when I'm adiabatic. So I see that this is going to be an issue, and I'm not sure how to solve it. In fact, now remember how I expounded at length about how it's important to know the absolute entropy and that we won't treat entropy as a relative thing like we will with G and H in the table on the back of the book? That's why. Gases? Easy, easy, easy. Where's my Bob calculator at 0 degrees K? I need to know the number, not the relative number. So that's one of the reasons that engineers went to all the trouble of measuring the absolute entropy of materials, not their relative energy as they did with G and H. So here's one thing. All right, so let's see how far we can get until we get to a point you can't make progress. That's my point. You hit a stopping point. But let me show you where it is so that we get flexible with this. All right, now maybe don't write this down. Let me show you a mistake a lot of you made on the test. And it's not exactly this mistake because it's not the same question, but it's of the same thing. Sorry, where am I at? Okay, so a lot of you on question 13, you tried something like this. NRT. So you changed V to NRT DT. You tried something like this, something akin to this. You can't. Now, actually, I'll give an example. When I do derivations, I'll actually show you the exact mistake you made. But I'm just pointing out to you, you made a mistake. A lot of you made a mistake that's akin to this. No. Can anyone tell me why I can't do that? Hint, it's the same reason I can't drop this term. T's not constant. This is untenable. Oh, maybe I'll just put a delta T. Well, now you're just making stuff up. I'm kind of tempted to do stuff like that, but that's not right. So, again, that's kind of a similar mistake that a lot of you made on the test. I'll actually show you exactly what that mistake was in a little bit. Okay, so, tell you what, I can deal... and now do I want to deal with this like I did there? When I did VDP? Can I do this? Can I do that? Same thing. All right, can I just turn this into, can I turn at least this term into minus the change of, the reversible work? Can I do that? The isothermal reversible work? The isothermal reversible work?
No.
No, why not?
T's changing.
Because T changes, right. So we have to, all right, so I'm going to start with this guy. And I'm going to figure out, I'm going to deal with that. And let's see how far I get. And again, this would be good practice. Okay, here's what I did. I just did this is why I'm a little bit sketchy today, because I was just figuring this out. I realized I could do this, and this is actually similar to what a lot of you did on the test for that last question. If you answered it alternative ways, you may have noticed that if you answered any of my questions but in an alternative, legitimate way, it wasn't counted as correct, and if not, come see me. So I realized I can make this substitution. Okay, now this guy, then again, I'm doing perfect gases because I'm not that unfriendly, and I can make this transformation at this point. And then this, all right, minus PdV under adiabatic reversible conditions. Again, I won't throw irreversible. I tend to stay away from it. It really is a Bismarcker. So let's talk about it again. Adiabatic. Let's say it's reversible. What's minus PdV? It's what? Well, hold on. Is it negative work or is it work? It's work, right. I impact with that negative sign there. Okay, and if dq is 0, then what's work? du. Okay, du is, what's the change in, what's the change in u? Adiabatic. It was the question, it was the little question on the test.
CVDT.
CVDT. So I'm not gonna, here, I'll do it this way. Sorry, I know this may note taking kind of a pain in the ass, so sorry about that. All right, notice that this is then CP dt. Right? I just factored out the change in temperature. Okay, not too bad, not too bad. Okay, let's try the same trick with this. Minus change in ST minus plus TDS. Sorry, that's awfully crowded. Well, that's why we have videos, right? So, okay, now, let me explain that a little bit easier. Okay, now, TDS, we're reversible. Again, we'll do adiabatic reversible. What's that guy? Yeah, 0, because the change in S is 0. Here's another way to think about it. What's heat? 0. Heat 0. Give me a formula. Oh, a really simple one.
S times
T times change in S. Okay, you need a reminder. That's okay. All right, so again, this is reversible heat. But we're adiabatic, 0. So that term's gone. Okay. So now, all I have to do, okay, so now I've got this minus S change in T. Sorry, let me do this a little bit nicer. Now, here, see, I'm in the same situation I was here, and I had a nice out. What's my out here? Right, I had PD equals nRT, because I'm the perfect gas. What's my out on T times S? Win a Nobel Prize if you can figure it out. Which means that, no, right, there's no good way to do it. I don't have a perfect gas equation with an S in it. That's why. It is in there. It's just hiding itself. Just like, our ds dp at constant whatever is equal to dp dt, all the Maxwell. Right, so it's in there, but it hides itself. And because S does not explicitly appear in a perfect gas equation, I can't, this trick here is great. I don't have one. I don't have one. Oh, here's another problem. Let's say S is constant. Does S change with temperature? Of course it does. Can I hold S constant? Of course not. And it changes a lot. You can't ignore the fact that when you're changing temperature, which you will do when you're adiabatic, S is changing at the same time as T. That makes this untenable. What you have to do is, you have to get a computer. You have to get a computer and say, model, okay, so my adiabatic compression, my gas will heat up. And I've got the formulas to do that. Again, we'll do adiabatic reversible. And I got those formulas, TF over TI to the CV over NR. I've got all that. I know what my temperature will be. But so what I'm going to have to do, though, is I'm going to have to figure out how to integrate this numerically. I can't do it analytically. Analytically means I derive a formula. Numerically means I write a computer program. And the way to do it would be to discretize this into little chunks of changes in temperature, where I figure out for every degree change, so what's my change in S? And I have to, again, model it with a computer and have it discretize temperature, figure out what S is at every temperature, and I already know what T is at every temperature, over that temperature range that I calculated, and then I can get this term. But I cannot do it on pen and paper, it's impossible. So anyway, just a little exercise in derivations, but to show you, I'm not asking delta G or delta A on adiabatic because you can't actually do it. And also to remind you, this is why we need absolute entropies. And we don't need that for anything else except that because it appears right there. So anyway, now I'm not going to go over this, but if you want to on your own, you're going to run into the exact same problem because you have the exact same term. But what's kind of neat, you're actually going to get CVBT for change in A. But again, it's still unanswerable, in case you can't see that. So, okay, derivations. Let's do lots of derivations. I got plenty of time. And I still hope at some point, what is this? I don't care about this. I hope at some point I can start to cover things you're going to get in 346, some of the extra mathematical stuff that would help put you ahead of the other people that were in this class, wink, wink. But I'm thinking that will be after the second test, which is probably a little bit better anyway. Okay, derivations. There. So let me do the exam question, and let me show you where a lot of you blew it. And let me show you also where a lot of you actually did clever things. Okay, so a lot of you, and the question was the H, BT, and constant T. And what I thought you would do, I'll just write it out, because hopefully you're okay with this. Now, I set you up, and what I thought was a relatively easy way. Some of you figured out a clever way, easier than what I was doing, easier than what's on the exam. The exam, I wrote it out this way. Again, I gave you a starting point. I told you I would do that. But it turns out I didn't realize, those of you who did this an easier way, it was very clever. It was easier than what I had done. And I'll show that in a minute. But this is what I was kind of hoping you were going to go to. I already told you this was 0. You proved it on the last homework, or this one, I don't remember. What I wanted you to do was see that this was minus V, and this is obviously plus V, which was 0. Now, what did some of you do? Okay, so that's, I mean, you can see this was a very easy question. Some of you did this. All right, so I gave you that this was 0, and then you took P, and then you inserted for V. This was clever, but unfortunately it's not right. You inserted for V, NR, let me make sure, NR, yeah, so you decided that temperature was going to change. So you inserted NR change in T over P. And then you still had the dP at constant T. And then you did the same thing over here. Okay, let's make the change in P, NR over V, change in T. So I see NRT over V, which is P, except that I had a change in P. And then you said that was 0, and then that's 0. Okay, lost a lot of points. Of course, you may be asking, why is it wrong? So wrong. Don't make a mistake. Don't look at this in your notes and say, oh yeah, I could have done it that way. No, you can't. There's a simple explanation as to why. I know it was a bit subtle. I know that when I first saw some of you do that, I got a little bit lost myself, because it kind of looked okay. And it actually took me up until now to figure out exactly why it's wrong. And it's kind of simple. For one, notice that, look at the last term, VDP over P. That's obviously volume. That has to be volume, it's not zero. You made it zero. That by itself says it can't be correct. There's no way that can be correct. But look here, I got a better way, a little bit better way to show you that that is not the case. So what you did is you took the P, I'm sorry, no. I'm going to do the second term. dp, constant t. You took this term, and what it really is this, nRT over t squared, which is minus nRT over p, which is minus b, which is what I wanted you to do. When you said that was equal to nr, looking at the second term, nr, dt, dp, constant t is 0. No, it's just fundamentally wrong. That's why you can't do that substitution. So anyway, because I didn't want to, not trying to poke fun at anybody, but I just wanted to, you know why you can't do that. It's just, it ends up just being just this simple. So be careful. If you find yourself wanting to do something like that, here's a way out. Check it. Check whether the term you started versus the term you turn it into, you can do them. See if it works. Okay, so it doesn't. So that's why this doesn't come out. Now, what do I want to do? Okay, here's a clever thing that a lot of you did. You ignored what I gave. Well, you partially did. So you took this, the term I gave you in the middle, and you divided by p, constant t. Again, this is automatically 0. I already told you it was 0. That was gone. And you said that this was equal to nr changing t. Sorry, why did I do that? Sorry, p. Now this was legitimate. This is actually a perfectly acceptable way to answer this question, was to do the whole PB equals nRT trick. This actually does work. So, and that's actually why when I saw people do this, I got a little twisted up myself. Because I'm like, yeah, that kind of looks right. It kind of looks right because this is correct. And again, if we expand it like I had done up there, it is 0. So this term does turn to 0. Whether you do it this way or that way, it's got to be 0. So that was correct. If you did it, I give you full credit. If I didn't, that's a mistake. Please come by. Oh, sorry. Oh, excuse me. Let me fix it. Let's see. What else do I want to do? Okay. Just more examples. Just let me throw all the letters of the rainbow at you and just work as many questions as possible. And I'm going to work a really hard one. And it's going to be easier than the one you got one really hard derivation on the homework. I'm going to work a harder one, so the one on the homework will be a little bit easier. Actually, be a lot of bit easier. But in the meantime, let's do the H, the, and you see, I got a million of these. Now, my guts, I can just fly on my instincts. Always remember that the change in H is one that's all positive. T, constant T. Again, now this would be not the life, universe, and everything. This is easier than a derivation that belongs in that section. This is clearly easier than a derivation that belongs in the derivation section. So again, this is an easy one. Okay, let's do the right-hand side. And again, P is a constant over V. So the derivative is minus a constant over V squared, minus nRT V squared. And that is, that's going to be minus T. So again, I'm working downward. And now I have to do a side derivation. I have to do a Maxwell equation. All right, so again, a derivation on one side, we have to do a derivation on the next side. Obviously, I have to get rid of the SDB. I need a Maxwell equation. And I'll tell you that. If you look at your homework, I said, oh, you're going to need a Maxwell equation. Okay, what energy function should I pick? Hmm? Remember, I've got 4 Maxwell equations that come from 4 energy equations. It's the 2 on the bottom. What is a function of V and T? A, right, you want A, very good. Now again, you can just write them all out. And that's the one that's all negative. And I'm going to do my trick, blah, and blah, and blah. The S, the 2 negatives will cancel. The S dV a constant T. Yeah, see, got it. It's dP dt, constant T. Okay, dP dt a constant V is mR over V. T times, oh, sorry. I'm trying to be exact. Is equal to P minus P. There you go. Anyway, pretty simple. Maybe this is a little bit harder than just the section before, like the universe and everything. Maybe, because I do try to go a little easier on the tests than homework. But just to get another example. And so, do get comfortable with these Maxwell equations and ask you to derive them. If I do that, I would, if I need you to use one of these, I will probably put them in the cheat sheet, because this is a small cog, in my opinion. It's half the question. And if you can't get this factoid, you're going to lose half your points. And I don't want you to lose half your points. You're losing half the points on all your questions, you're getting an F. So if this happens, if this appears on the test, look for Maxwell equations in the back if you can't do this. This is a good way to make sure that you're right. Besides, it's obvious if you're right. So anyway, that's the kind of thing I think I'll do. Let me see, what else do I want to do now? Okay, yeah, you're going to love this. This is similar to a homework question, but it's a real, this one is unpleasant. Very unpleasant. Let's do the same question. But, van der Waals. All right, van der Waals equation. Van der Waals, you bet. Now remember, you know that H will actually change a constant T if it's a real gas. We did that in Joule-Thomson. Right, so we saw that. It wasn't quite set up that way, but I know that this is true for a perfect gas because I use the perfect gas law. If I don't use the perfect gas law, guess what? I may not get 0. That's bloody likely. And now, Joule-Thomson wasn't quite the same way. I didn't quite ask this question. I actually looked at H as the change of P that I'm doing V. If P is nRT, so I'm using the N version, squared over V squared, is that right? Just going on hand. Okay. So, okay, let's start where, I'm going to go ahead and just do what I already know, which is up there. Let's see, I've got T, oh, I kind of really screwed you guys, dP, dt, I see I was jumping steps, and then I've got plus V, dP, dV. Okay, and again, the question that I gave you, which is a change in U with the van der Waals equation, is actually going to be slightly easier, actually a lot easier. So again, this will not turn into, minus P. This does not turn into minus P, and this does what it does. All right, so let's do this guy. This isn't bad. This one's easy. NR V minus ND. I'm doing the derivation in my head. Right? This is a constant times x. There's no x here. This one is unpleasant. Okay, let's do this one. Now, again, don't forget that this is nRT times Vn minus B to the minus 1. Right, now that makes, I always have a much easier time when I'm doing 1 over x, when I say it's x to the minus 1. That I get. So this is x to the minus 1. So that means you're going to take out the minus sign, nRT over Vn minus b, v minus nb squared. Okay, that's really not, it's not that bad. It does give me a little bit of a pause. And yeah, I've been doing this for years, but again, it's basic calculus. First month you were doing this. Okay, and this is a constant times x to the minus 2. So that's going to pick up a plus 2, a and squared, and then I'm going to have b to the minus 3 over b to the 3. There we go. And what is easy on your homework is that you're not going to have this, by the way. It's going to actually go away. So that's me telling you what's on your question. Because I don't want it to be too blindingly difficult. Okay, so now let's keep going. Right, this h of b, t is nRT. First term has just come back, that's nice. Sorry, minus b times nRT over v minus nb squared plus 2a n squared over v squared. Right, I just distributed the v. And now what do you do?
Let's go back.
You do what?
We get the next one to the back.
No, the answer is do nothing. Stop. Some of you, not many of you, thank God. Some of you did some factoring and you got it wrong. Don't do that. You're giving me wrong answers. I can't give you full credit. I wasn't cruel at all, but I can't give you full credit. Now, how close does it, what does this look like to you? Does that look like a big number? Now, I just want you to look at this and appreciate how different are these two numbers? Are they terribly, terribly different? No, because if NB is small, like we're talking about a big volume, then I've got volume over essentially volume. Returning nRT over Vn minus b, nRT Vn minus b. V minus NB, sorry, I'm talking too fast. Usually I don't work with the N version, I use the Vn version. Anyway, you know that. This is not bad, right? So I see that this is damn well close to 0. It's not quite 0, but it's very, very close. And so approximately this is 2a n squared over v squared. And what's nice about that is, again, let's say I ask you this, one second. I ask you this, is this consistent with our previous result for perfect gas? Perfect gases was 0. Is this consistent with that? Why? What's A for a perfect gas? Huh?
Molecular attraction.
0. Right. Because perfect gases don't have molecular attraction. So that's 0 for perfect gas. So again, this is damn likely a question I might ask in an early section. Instead of having you work it, this would be a really hard derivational question. I would not go this hard on the next test. This is really a lot to throw at you. It's not hard, it's just too long. I won't ask this type of question in the exam, I assure you. But I am bloody likely to say, okay, if this is approximately that, is it truly consistent with a perfect gas? Of course it is, there's no A. Now remember, there's no B either. If there's no B, I've got B over B squared. And then this term is also 0. So even if I don't make this approximation, it all works. So anyway, I got one more. I have time for, I've got about 4 minutes left? Just one more, because it's really similar. So this is the hard one. This is the hard one on your homework. Let me give you another one. That, again, this is very similar to one of your homeworks. And then we're done. And like I say, one day we'll get to that quantum stuff. And I'm going to go over some trigonometry and imaginary numbers. Because that's going to come up a hell of a lot in PChem too. So we'll do that after the second test. Okay, again, I'm throwing letters, I have a menagerie of letters. I can ask anything. What is this? What is that? Because I can just, I have so many letters to work with, I can just come up with stuff all day long. Okay, so, start the SDT. Okay, I'm starting writing delta G. So now that we've covered this stuff, as opposed to as opposed to U plus TS, U plus PV minus TS, this is a much better starting point. Constant S. Now, how did we deal with that? Remember when we did those constant entropies? It's just what? It's just one. It doesn't matter. This matters a hell of a lot. Okay, so let's solve this guy. Now, I happen to know, where do I do this? I gotta remind myself. I know that I'm seeing T and P, which makes me think that enthalpy, because pressure and enthalpy seem to always go hand in hand. In H now, this is adiabatic, reversible. And so I know that change in H is CPdT. And I also know that's, let me make sure I do this right, TdS plus dVp. And so I need dPdT. Oh, geez, did not give myself enough room. dP. I'm sorry. dP at constant S. So this is how I knew, again, to go with H, because I knew that my S term would go away, because H is a function of S. And this guy ends up also being 1. So now I see that dT, dP, constant S, is the only guy standing, and then I gotta get rid of that CP. Okay, so this is minus S times V over CP plus B. Now, at this point, you're done, but I want to point out that it can be factored. This is kind of similar to what I have in your homework. I'm going to factor out a minus V, so I have S over CP minus 1. And again, now you're done. Now, to help you with another part of your question, we're done in actually early, oddly enough. Entropies per, so let's do these per mole, but I won't write it down, whatever, it doesn't matter. Entropies for gases, and have I done perfect gas? I haven't actually done perfect gas, so this is general. This doesn't have to be a gas question. But let's say this. It turns out that entropies of a lot of materials, a lot of gases, are in the 100 to 200 joules per k mole. CPs are, 18 to 30 joules per k mole. Okay, so this term, if S's are in the hundreds and CPs are in the tens, this is greater than 1, minus 1 is positive, times a negative. Right, so the question is, does this go up or down with pressure? You increase pressure at constant entropy, G goes down. So, what does that mean? It means if you build an adiabatic reversible machine, don't raise the pressure. Do raise the pressure. Right, do raise the pressure, G goes down, that's good. Okay, I'm done. Let's get out of here. I'm going to beer in my fridge. Oh, got to get it down.